problems, and apologize for the delay, right? So it's a pleasure to have here Alessia Ritacco. So she's visiting during this week. So Alessia's background is on experimental and observational cosmic microwave background. So she was a PhD student. Well, before that, she was an undergrad in La Sapienza University, and at that time she started to be involved in experimental projects related with CMB, in particular to the developments of M-kits detectors. And then she moved to Grenoble, where she was a PhD student under the supervision of Juan Macías Pérez, who some of us know for a long time. So there she was working on the development of characterization of a M-kit camera dedicated to CMB and galaxy clusters observations in the IRAM 30-meter telescope that is called NICA and NICA-2 after that. And she completed her PhD in 2016, 2017, more or less.
Yeah.
Okay. After that, she moved to Paris to work in the IAS, and there she was has been working more on the issues related with the characterization of dust polarization as a contaminant to the cosmic microwave background, and she will be speaking today about that. Before that, now she's moving to the OAC in Calgary, where she will start a new position. So the floor is yours, and thank you for presenting this talk today.
Thank you very much, Ricardo. It's a small problem. Can I put on the slide? There is an echo. Okay, thank you very much for the introduction, and I'm sorry that it delayed the start of this talk. It's a pleasure for me to be here and to present this work that I have performed in Paris with the people that are with the people that are listed here, mainly working at the École Normale Supérieure of Paris, and these concern the dust polarization spectral dependence from Planck HFI data. And I have used a new release of Planck HFI data to characterize this very strong contaminant for the cosmic microwave background polarization measurement. So this is my outline. I will start to introduce the scientific context from a very general point of view. And then I will go through the importance of the observation of the cosmic microwave background as probe of the primordial universe. And I will go into details of dust foreground emission for this detection. And I will talk about the constraint on the CMB polarization detection accuracy. In particular, the main topic of my talk and my work recently finished will concern a power spectral analysis by using the new release of Planck HFI data. So before moving to polarization observation, I like to introduce this because we talk about total intensity emission and polarization, and it's very worth to understand what is the bunch of information that we can recover when we look at the sky on different frequencies. Here, there is a collection of total intensity emission observed at different frequency that you have here, from radio to gamma rays, and you see from the this view of the of our galaxy, we can understand different properties of the emission if we look at the sky at different frequencies. So when we combine different observation of total intensity emission, looking at the full sky, what we obtain is this multi-frequency information that has been recovered by the Planck satellite, and it combines several observations from 30 gigahertz to 857 gigahertz. And we see that the amount of information that we can recover is very big about the galactic astrophysics, but also large angular scale on the sky. So now, why should we observe the sky in polarization? We already have a lot of information about the total intensity, and we can recover and test a lot of physics with the total intensity. But the polarization allows us to access to some processes in astrophysics and cosmology that we cannot probe in another way. In particular, I have listed here some of the probes that we can have when we look at the sky in polarization concerning the synchrotron emission, the dust emission, for example, and we can mapping the magnetic fields in galactic molecular clouds and understand the star formation process. We can trace Faraday rotation, magnetic fields on the surface of stars through spectral lines. And other effect, we can observe the quasars, galactic active galactic nuclei, and pulsar. And also the main topic of this talk, we observe the cosmic microwave background that give us information that are not available in another way. So the polarized light is usually described by the Stokes parameters that give the that are related to the polarization angle, and here we can see the Stokes parameters where we indicate the I as the total intensity emission, and we divide the Q and U and V. We describe the Stokes parameters that describes the orientation of the polarization light. So the Stokes polarization parameters Q and U give us the information about the linear polarization with this direction listed here, and the V Stokes parameter give us the information about the circular polarization. So I just introduced these parameters here that rely on the Stokes parameters to describe the polarization intensity, the polarization fraction, and the polarization angle. Because during my talk, I will talk about this parameter to describe the polarization light. So now at the beginning, I have shown what we have when we observe the galaxy in total intensity, at least on a part of the galaxy. And here I showed the Planck maps obtained at the lowest frequency in polarization of 30 gigahertz. And you have the high map, the Q and U map, which describes the linear polarization. And we have the highest frequency provided by the Planck satellites, which is also polarized. And we can distinguish very well from these two pair of three maps of I, Q, and U, the differences and what we can learn from the synchrotron emission, which peaks at lowest frequency, and about the dust emission, which is more important at highest frequencies. So if we look to the sky at all the frequency band covered by the Planck satellites in polarization, there are still missing bands here that cover only total intensity. We can distinguish the synchrotron emission, which is very strong at low frequencies, and we see the thermal dust, which peaks when we go at higher frequency. And the cosmic microwave background is located here. So you see that if we want to observe the cosmic microwave background, we need to know very well how to subtract these strong emissions provided by coming from the synchrotron emission and the thermal dust. So the cosmic microwave background represents the relic radiation from the very early stage of the universe. It has been observed as emitted 380,000 years after the Big Bang, and thanks to the observation of this radiation, we could have access to a lot of information about the primordial universe and establish a very good model for our primordial universe, which is called the standard cosmological model. This model doesn't answer to a lot of different questions that are remaining to us. And for example, the main question is to answer to what mechanism created this cosmic microwave background anisotropies that we observe and that eventually grew into stars and galaxies that we observe today. So in order to describe what happened at the beginning of our universe in the history of the universe, the inflation theory predicts a nearly exponential expansion of our universe, during which primordial gravitational waves have been generated and that left an imprint on the cosmic microwave background. So cosmologists today want to have access to this primordial universe, and this is the most accredited theory that could give us information about the primordial universe. So the main question to answer today on cosmology is the measurement of the imprint left on the cosmic microwave background by the primordial gravitational waves generated during the cosmic inflation. So the Planck satellites already unveiled the cosmic microwave background and subtracted all the emission that I have introduced at the beginning to show this cosmic microwave background anisotropies very well. It observed in temperature, so in total intensity, and also in polarization. But the sensitivity of the Planck satellites is not enough in polarization to have access to the measurements of the primordial B-modes that gives us the amplitude of the cosmic inflation. And you can see already that by eyes looking at these maps that the polarization it's very weak compared to what we can observe in total intensity in temperature. So the main question today is to have the measurement of the cosmic microwave background in polarization in order to have the precise measurements of the E-modes and the B-modes. This cosmic microwave background, E-modes and B-modes, describe a different direction of the CMB polarization and the results from a linear combination of the Stokes parameters that I have introduced at the beginning, which are the Q and U linear polarization. So the question is how to measure this very weak signal and how to probe the primordial B-modes. This B-mode signal can only be produced by primordial gravitational waves in the early universe, and if detected, it will give a direct proof that the inflation occurred. So I have shown the maps, but in order to understand how much lower is the amplitude of the cosmic microwave background polarization with respect to the temperature, we see here the analysis of the cosmic microwave background in the power spectrum, where we have here the observation that traced very well the cosmic microwave background in temperature, and that allowed to understand and to establish the cosmological parameters from density perturbation. And you see that already the cosmic microwave background polarization E-modes is very weak with respect to the temperature, and for the primordial B-modes, we only have a guess and we don't know which is the real amplitude with respect to this signal. But the cosmologists search for primordial B-mode signal in this part of the spectrum. So the observation of the cosmic micro-background in polarization for E mode and B mode will give us access to a physics beyond the standard model and give us the possibility to test the inflation theory. So as I have introduced at the beginning, there are two very strong foreground which cover completely the sky, and that we need to address in order to measure both the cosmic micro-background polarization E mode and the B mode, which is at the level expected and parameterized by this parameter here of 10 to minus 3. So there are two different instruments under development, which will reach the sensitivity for such a detection at this level of the primordial B modes. But in terms of data analysis, we need to address different topics in order to have the precision to reach this measurement. One of these is to understand the dust and synchrotron foreground emission. So the different technical challenges that we need to address for such a detection concern to build high sensitivity instrument, which is the case, for example, of the LiteBIRD satellites or the ground experiment, the CMB 4 under development. It concerns also to address the high control of systematic effects, and for this, a new device which allow us to measure the polarization has been studied, which concern the halfway plate device, and also we need to have a precise absolute calibration of the polarization angle. I'm working on these two aspects here, but today I will show you my recent work on foreground emission subtraction. So again, if we look at the sky on synchrotron emission, we have a lot of information here that we can recover. And if we compare with what we have from dust emission, it's completely different. So what is emitting in dust? What is emitting in polarization at this microwave wavelengths? So the mechanism of emission of the polarization comes from the dust emission, and you have here a sketch that shows that the unpolarized light is coming from here, and then the interstellar grain spin around their axis of maximal inertia, and their rotational axis processes around the magnetic field lines. So the polarization results from the grain alignment with the galactic magnetic field. And to some extent, these grain polarization properties are homogeneous, and the dust polarization tracks the magnetic field structures, which is related to the different direction of the linear polarization. So a way to describe a model that has been used and tested on Planck data is it is called the modified black body model, which describes the intensity of the dust emission here as a function of a black body Planck function modified, and which depends on the temperature of the dust emission, on the spectral index beta, and the optical depth. This is a canonical model for dust cosmic signal in intensity and polarization. It is surprisingly accurate, but it is not linear, and we can find SED distortion, spectral energy distribution distortion, which is the topic of my talk. So on the previous Planck data analysis, the Planck collaboration could extrapolate the dust mean spectral energy distribution determined for multiples higher than 40, so at small angular scale. And here you see this spectral energy distribution computed for the E mode and the B mode compared to a model which is shown in gray, which is the one that I have shown before, the modified black body. So the dust SED polarization from Planck 2018 results is remarkably well fit by a single temperature modified black body emission, but these data were limited by the signal-to-noise ratio in polarization, so we couldn't have access in this part of the spectrum where we search for primordial B-modes. Anyway, these results brought a significant advance in constraining the dust models in astrophysics and as CMB foreground dust components separation methods. So in the now we'll start to talk about my work, trying to understand how to model the SED distortion of the modified black body model at NSR, which is not limited by the noise. So this is the central part of my talk and my work, and this work will be published soon. So I just finished the data analysis. For such a work, I moved forward to the Planck 2018 release of the HFI maps, the high frequency instrument maps. And I have used the what is called the SROL2 release, which is the updated software used for Planck, and which addresses different systematic effect improvement and give us a better reconstruction of the polarization maps for the 100 gigahertz, 143 gigahertz, 217, and 353. So the maps that I have used in my work are shown here, where you see the Q polarization and the U polarization maps. And you see how the structures of the emission polarization changes from 100 gigahertz to 353, growing up in terms of dust emission polarization. So as I said at the beginning, the polarization data of the Planck satellites were limited by the signal-to-noise ratio and are still limited by this. So in order to compare with the model that is understood and that describe the spectral energy distribution distortion on the full sky, I compared the polarization maps extrapolated for the SROL2 release of the Planck data with the synthetic model that I built from the total intensity information. So the simplest way was to take the equation here that I have already introduced, which describes the dust emission with the modified black body function. And then I took the extrapolation of the Planck models, which extract in total intensity the temperature and the spectral index. So these temperature and spectral index maps are used in this formula here to have the to extrapolate what we expect from a modified black body function of the intensity at different frequencies. So from 353 gigahertz, which is our pivotal frequency, to 100 gigahertz. So the extrapolation to polarization of this model is to use as reference for dust emission polarization the Planck map in QAU reconstructed at the frequency of 353 gigahertz, where we have the peak of dust emission. So the model are created on this, calculating this INU. I'm sorry, here is ED, but ID is the same here. So ID is function of nu calculated with this formula and using these maps. And we extrapolate the Q model and U model by assuming that we would have the polarization fraction coming from the dust emission calculated at 353 gigahertz. So this synthetic model allows us to reconstruct the maps that would have if the intensity data could be transformed to polarization by using the modified blackbody function. So this two pair of data represent the Q here and the U here from 100 to 2017 gigahertz. Just remember that I used the 353 gigahertz as a reference frequency, so I extrapolate the dust emission at lower frequencies. So in order to compare with the data directly, I have to include to the model also the instrumental systematics and the CMB, which are part of the polarization data. So the analysis that I have performed is performed on the power spectra analysis by using a mask defined on the full sky to understand how the polarization dust emission varies if we take most of the sky by excluding only the central part of the galactic plane and going to higher latitudes, considering 80% of the sky. So this fraction of the sky are used in the rest of my talk to compare what I can obtain. So the cross-power spectra analysis have been performed on the maps that I have shown before, where I have directly the polarization data from this release of Planck HFI data and the model. So what I do is to extrapolate the SED, the spectral energy distribution coefficients by considering the cross-power spectrum between the dust maps that I extrapolate and for the model and that I have from Planck data with respect to what is observed at 350 gigahertz. So these two different lines here show the SED averaged on the different sky fractions. So you have here 80% of the sky considered, 90% and 97. And what I compare is the SED with respect to a modified black body. So if what I observe on polarization is exactly described by the modified black body, I should have one everywhere. So it means that the modified black body can describe the dust emission from 350 gigahertz to 100 gigahertz. So the two different lines here represent two different models, but just look at one, we see that when we have 97% of the sky, so almost of the sky, we have here what we obtain in polarization in solid line and what we observe, what we can extract from a model based on total intensity, which is shown in dotted lines, and we can compare what we have. So we are around 1, so it means that already the modified black body is a very good model, and but we have a discrepancy from what we observe from polarization data directly and what we have from a model based on total intensity, SED variation. So going to the less sky here, for example, for this model, this discrepancy is high if we compare and we extrapolate polarization from total intensity. So this already show that models based on total intensity cannot reproduce directly the signal observed in polarization light, which is a very strong bias for the current way to model polarization emission. So far I have used all the information recovered by polarization on all the maps. But what I want to understand is that if there is a spectral energy distribution distortion of the dust emission, which can be a very strong bias for the detection of the cosmic microwave B-modes data signal. So in order to address this part, what I consider is to extrapolate residual maps. So I take the polarization maps that I have, and then I subtract a medium SCD, a mean SCD calculated on the sky fraction considered. And what I left, what I have at the end are the residual maps, which shows that I'm not completely modeling the polarization signal if I consider just to average on all the sky or almost all the sky the SCD distortion of the dust emission. So here, from the top to the bottom, we have these residual maps that give us the variation of the spectral energy distribution from 100 gigahertz to 217 gigahertz, where we have more dust emission. Here we have the Q data, and here you have the U data. So, of course, in order to compare the polarization data and the model that I have built for comparison, I used to do the same calculation of residual maps from the data and from the model. So here you have the first part, so the data that I have already shown before, and here we have the maps, the residual maps extrapolated from the model that I have built from a modified black body function. So you see from the maps already that we can find some structures. It's a bit confusing here, but if we compare only this one and this one, we see that there are structures that are comparable and there are also differences. Of course, from the maps, it's very complicated to compare. And for this very weak signal, the best is performing the power spectral analysis by considering only polarization data and the correlation with the model that I have explained. So for all the frequency, for 100 gigahertz, 143, and 217 gigahertz, I have calculated the E mode power spectrum and the B mode power spectrum by using the maps that I have shown before, so only considering the residual maps. On the top here, we see the correlation between the two different data sets of polarization data, which are called ofthe emission 1 and ofthe emission 2. And on the second row here, we have the cross correlation between the polarization data and the model built on the modified black body function. We see that either for the E mode or for the B mode, there is one order of magnitude difference when we have the correlation between data only and data with polarization. So of course, already from this plot here is also very difficult to understand if there is a significance on our detection. And for this, in order to understand better, what I have done is to calculate the amplitude of this cross power spectrum for multiple that goes from 4 to 32. So for each frequency, what I have, it's a mean of the cross power spectrum that I have shown. So I have 1 point for each frequency. As I have shown before, I have two different models. Sorry, I have two different models to compare, so Commander and Genilk, but what you so what you have is the comparison between what we should have only in polarization, which is shown on solid lines, and what we have when we cross-correlate polarization with the model based on total intensity data. So going from 97% of the sky to 80% of the sky, we lose correlation between the polarization data and the model. We see that if for almost all the sky, the model based on modified black body on total intensity can approach what is observed in polarization, when we go to 80% of the sky, we completely lose the correlation, and there is a very large gap between what we observe in polarization and what a model can extract. So the models considered that are currently used are not enough to reproduce the spectral energy distribution variation of the dust emission detected in polarization. So another way to approach this problem is to consider always a modified black body function, which is what we know for the dust emission, and considering a Taylor expansion of this modified black body emission law. So if I consider the work that have been performed on a mathematical expansion of this law by all these people here, I should have a description of the residual maps observed, which can be described by a small fraction of the moment expansion of this law here with respect to the spectral index beta, and another part which with respect to the temperature T. So that's what is described for maps, but in power spectra. So we can divide the emission, the Taylor expansion of the MBB on these three different functions that depends on the spectral index here, on the temperature here, and on the cross correlation between the temperature and the spectral index. So what I have tried to do is describe, so fitting the polarization data of the residual maps detected here in red for the E mode and in blue for the B mode. And I have tried to fit the power law observed with these three different perturbation components of the modified black body emission law. So at the end, what I have is that for the first case, so the derivative compared to with respect to the spectral index is the one that describes more the behavior of the polarization data in for a fraction of the sky of 97%, but it becomes very far from what is observed when we go at a fraction of the sky, which is 80%. So this moment expansion barely can describe the behavior of the polarization data, but is completely far from describing what is observed for the BB data, which are shown here in blue, and that appears flat when we go to the 80% of the sky. So from this analysis, what we have learned is that we didn't understand everything that we observe on the sky. So we need, in order to describe what it is observed in polarization, we need an additional SED component. Otherwise, we will take models based on total intensity that will strongly bias the cosmic microwave background polarization detection. So a theory that has been formulated by Tassis and Tal, it is that we didn't understand and model very well what is the dust emission. Actually, all I have described by considering an emission law based on modified black body considers that everywhere on the sky we have only one cloud emitting with the temperature and a column density and the spectral index. But what happens if the polarization comes from two different clouds which are oriented one to each other with a different angle? So the assumption that everywhere on the sky we have the same cloud is it's not the reality maybe. So these people have addressed this problem mathematically, and they have considered that the relative contribution of two different clouds will change between frequencies due to the temperature dependence of the black body part of the dust spectrum. So this will cause the correlation of the polarization pattern from 350 gigahertz to 100 gigahertz. So we cannot extrapolate directly what we expect at lower frequency from the 350 gigahertz, if this is true. So in the work that I have performed, I compare this approach. So I try to address this question by considering only the dependence on the polarization angle. So the assumption and the hypothesis that we have done is that if we can extrapolate the dependence on the polarization pattern from the polarization angle only, we will see the correlation of this polarization for different frequencies. So I built here, I try to isolate the polarization angle variation effect along the line of sight, and I create two synthetic Stokes Q and U maps, which depend only on the C, which is the polarization angle. And for the same reason as before, I want to look at the impact of this polarization angle effect variation along the line of sight on the spectral energy distribution variation. So on the same way that, as before, I calculate the residual maps for these two synthetic Q and U maps. So in this plot here, I show what I obtain when I consider the polarization angle variation. When I'm on the galactic, I'm considering almost all the sky, and I'm on the galactic plane where all I have said is correct. I mean, the molecular curve depends on the temperature, and we know very well how this temperature density fluctuation can produce the emission in total intensity. Everything is understood. So the polarization data show that we have this kind of power law, and when we consider the polarization angle, which is shown here in dotted lines, we don't cover these differences here, which shows that the polarization emission here is basically due to the molecular clouds and the dust emission in the galactic plane. When we go to highest latitudes and we consider less sky fraction, this polarization angle effect becomes important. So we are going far away from our galactic plane, and the polarization angle appears to cover the gap between the polarization detected on the data shown in solid lines and what we extract from this angle effect. So this kind of effect is not considered now in the current CMB dust foreground modeling, and we show here that is very important effect that could be also even more important when we go at highest latitude, where we search for the cosmic microwave background polarization signal. So surprisingly, when I add all these effects, so I have studied what I have if I consider a model based on total intensity variation, And then I isolated the effect from the polarization angle variation. So surprisingly, when I add these two effects, so I create a cumulative effect, I reach what is observed on polarization data. So in this case, the dotted line here consider the cross correlation coming from the model on total intensity plus the polarization angle effect. And you see that from the 90% of the sky to 80% of the sky, we reach we can reach the signal observed in polarization. So this is the conclusion of the work that says that yes, we can describe the dust emission as variation of temperature and spectral index, but if we not consider polarization angle variation, we will have a very strong bias on what we want to observe from cosmic microwave background. So in conclusion, the primordial gravitational wave detection from CMB polarization requires unprecedented sensitivity from instrumental point of view and a very high control of the systematic effect. A very precise, requires also a very precise polarization angle calibration and a very precise subtraction of CMB foregrounds, because we are searching at the very weak signal in the cosmic microwave background. So the results of the work that I have shown, we have presented, shows that the current polarization dust foreground models are strongly biased, and this polarization angle variation along the line of sight is the major contributor to high latitude spectral index variations. And so if we want to have an unbiased detection of the cosmic microwave background B-modes, we need to create new dust models accounting for this effect. Thank you very much.
Time for questions. We start with questions in the room. So anyone in the room is willing to ask any question? Alessia?
So I was wondering in the model of the moment expansion, so wouldn't it be possible to increase the number of to go to higher orders in the expansion in order to try to improve this modeling, or that's not a possibility yet?
Yeah, it's something that is performed by in a work of Vache et al. But I think you have to compute a very large amount of orders to reach the convergence of your model. And just a few days ago, they published a new modeling, including this polarization angle effect. It comes out from a discussion that we had, and that they found a way to mathematically express what is expected from polarization angle variation along the line of sight. So there are two different approaches, but the one that's more relatable is the one that considers also mathematically the polarization angle variation.
Can you hear me? Yes, very nice talk. Indeed, my question is related also to that, because conceptually, I think in this moment expansion, what you are treating there essentially is the variation of the SCD in intensity, because in your modeling, you are basically assuming that the polarization fraction is constant. So the way I see that, I mean, the fact that the effect that you are calling rotation of the polarization angle essentially is a change of the polarization fraction. So what I understand, I mean, basically in your basic modeling, the equations that you had before,
yeah,
you are assuming that the polarization fraction is constant. And this is showing that essentially this is changing the frequency.
Yes, exactly. It was a way to compare with something that was already known and used, because now we build models based on this total intensity variation in the sky. And the comparison was just to see, okay, if we are able to describe everything that we see in total intensity as what we should see in polarization, we can cross correlate directly. But this work showed that it's not possible because there is something missing. Then we described it as this decorrelation effect due to the polarization angle variation. But the very important message is that we have to consider an additional effect to the current model to be able to describe what is observed in polarization.
I got lost a bit in this point. I understand that then there are like you did two approaches. You first modified the beta, the slope and the temperature of the black body, modified black body spectrum, intensity. You assume that the ratio of Q and U over intensity was conserved throughout different frequencies. You extrapolated that, and that didn't work, right?
Yeah.
And that you did on real data, because you had, for every pixel or every amount of pixels, you could compute what was the particular T and B values in every place.
Yes.
And that didn't work. But then you show this slide. And this slide is showing how the SED is changing with changes in spectral index and temperature. So in some sense, this approach is similar, theoretical, but similar to what you did in your very first part, right?
Yes. Well, this is a model based on linear expansion of an equation. So in the other case, I take two different models in map, so in pixel space, and the two comparison are reliable, are the same thing as you said. But this one with several order of magnitude, several order of expansion is what is currently used. So what I wanted to do is to compare directly what I would have by considering only theoretically. So in both cases, it didn't work. If I take only the equation expansion or I take pixel space, it didn't work, the correlation. So what is completely new is that we could go far away and for the first time measure the polarization data.
That's my next question, because if you move forward a few slides, then you write the correlation keep going.
Yes. No, this one.
No, this is the theory still. But when you introduce the
no, before
one,
maybe.
Yeah. No, I was referring when you do the polarization angle, right?
Yeah.
Here, this gamma, which is depending on frequency, this tells you actually the amount of change in the angle of polarization somehow, right? This you predict, this you can predict, or you fit on the data. In the next slide, when you compute the cross or spectra of the residuals, after assuming some value of this gamma p, how do you find this gamma p here?
I found this gamma p from here. This one. So the gamma p here gives the dust mean SED. So compared to the cross correlation between the dust maps on Q and U at 100, 143, and 117, cross correlated with the 353 maps, allow us to extrapolate this SED variation. So I estimate this gamma p here from this. This is I take the average of this cross correlation in the same multiple range, and I do the same for the models. So separately, I don't use the same SED. So that the SED calculated models is dotted here, and on solid line is the gamma p.
Okay.
So I assume.
So sorry. So this D stands for E and B, right?
And
B. So in this cross correlation, in this ratio.
D stays for Q and U. Because when you do cross correlation, you obtain E and B. Okay. I forgot to put here on the X6 will be either E or B.
So in this sense, the extrapolation that you do at the end for computing the rotation and polarization angle, or the change in polarization angle, is motivated by the data itself from this curve.
I need to extrapolate the Q and U synthetic Q and U at different frequencies. So I assume that I have an average SED, which is true for the polarization data and should be true also in the case of synthetic model based on polarization angle.
Maybe there are more questions. Let me check out here in the chat. No, these are just the students. Let me just minimize, not minimize, but there might be some questions in the YouTube channel, but there are nobody. So hold on. Okay, so this is the last chance to ask any question. If not, let's thank Alessia again for his great talk.